about this session. So without further ado, I'm really happy to introduce today's speaker, Dmitrii Ustiugov. Dmitrii received his PhD from the University of Edinburgh and is now joining ETH Zurich as a postdoctoral researcher. And his presentation is turbocharging serverless research with STeLLAR and vHive. So Dmitrii, over to you.
Thank you. It's great to be here. Can you enable sharing the screen?
Give that a try.
All right, thank you. Can you see my screen now?
Yes.
Nice. So thanks a lot for having me here. And today I'm going to talk about vHive, the framework and ecosystem for serverless experimentation that we developed. And I'd like to share our latest research results. Some of our team members are here in the call, so it would be great to have an open discussion in the end of the talk as well. So serverless allows service developers to focus on writing their code as a set of functions, whereas the cloud providers take care of all the heavy lifting, which is automatic scaling of function instances according to the traffic changes. This labor division boosts developers' productivity, allowing fast time to market for their products. So say the developers need to write a video analytics application with two functions. First, the first function decodes frames, which comes from a camera in video fragments from the camera, and it invokes the second function to recognize objects in this frame. So in serverless, this application can be written with two functions composed with simple function calls, and I'm sure everyone is familiar with that. So this flexibility also comes with pay-as-you-go, combined with pay-as-you-go billing, where the developers only pay for the cloud resources, which functions actually use. So this is why serverless clouds simplify the programming burden and also have cost advantages compared to the conventional clouds. From the serverless cloud provider's perspective, the situation is completely different. And to accommodate changes in the invocation traffic in front of each function, the provider scales the number of instances of each function on demand. So a function can have from 0 to virtually infinity number of instances, which can change at any time. Making these scaling decisions timely and intelligently is key for overall cloud efficiency. So for the providers, serverless raises a lot of challenges from the perspective of the infrastructure. So what is the current status of serverless clouds? Serverless main advantages are in its simple programming model and flexible billing. However, today's serverless clouds provide lower performance and reserve more cloud resources than it is necessary. One of the key problems is its slow reaction to load spikes because it takes time to launch more instances of functions on the fly. As a result, providers tend to over-provision the number of instances according to their understanding of the cost-performance trade-off. And the second example of a serverless problem is its inefficient communication across functions in a service which is related to their stateless nature. Providers scale instances on demand, disallowing instances to hold or share state so that any instance can process any invocation. And these are entire research directions with a lot of papers coming out every year. So there are a lot of problems, but there are also a lot of other problems associated with the programming model, security, and so on. But for us, for academics, one of the key issues to date is that serverless providers rely on proprietary infrastructure, preventing systems researchers from doing their job efficiently. So these are all big challenges, and this is what we were focusing on so far. Our work covers all three key types of systems research, from benchmarking leading commercial clouds, experimenting across the entire serverless stack, and innovation across system layers. Our first work in serverless characterizes the state-of-the-art cloud offerings, and it was first to compare cloud performance across different providers, even with proprietary infrastructure. And this was acknowledged by the leading Amazon engineer, Mark Brooker, even before the paper got published. To analyze various components of the deep serverless stack, we introduced vHive ecosystem, for which we had a full day tutorial at Top Conference in Systems this year, ASPOS. Everything is on YouTube, so you can take a look. And there are a lot of universities which use vHive today for their research studies and also for coursework. At the same time, we have a lot of collaborators and contributors across many companies. And this keeps growing over time. And many of these companies have research groups, even several, which use vHive for either evaluating their accelerator products or to understand the server's workloads. Using vHive, we innovated in several systems domains, with the first work called REAP Snapshots, which improves the reaction time to traffic changes by accelerating launching new instances of functions by using function working set aware snapshots. This REAP technique is already supported in the latest version of AWS Firecracker. And the second work called Expedited Data Transfers, or XDT, introduces a novel cross-function communication fabric for serverless clouds, which enables data transfers at the wire speed in conjunction with existing serverless autoscaling infrastructure. And this is the work we actually prototype in Knative. There is another work which is called Jukebox, which got recently published in a top conference, which talks about specializing microarchitecture for serverless workloads. So in this talk, I'm going to start by presenting the performance analysis of the commercial clouds that we did with a tool called STeLLAR, which we devised. And then I'll talk about the experimentation framework that vHive represents, and show you how to address the real-world problems, whether it's a cold start or serverless functions communication. And I'll briefly touch about the future work for future directions of the ecosystem. So it's essential to start with benchmarking the existing clouds and understanding which problems matter for both the production teams and conceptually for the academics as well. So we started by examining what the modern serverless clouds are today. And the first important observation is that serverless clouds today, even though they are from different providers and run different infrastructure, they all have the same fundamental architecture. Any of these clouds which we studied have three foundational components, namely the cluster scheduler, which is on the way of all incoming invocations, which selects or spawns the appropriate instances for each function invocation. Functional instances themselves run on a fleet of worker nodes. So to launch a new function instance, first a function image has to be retrieved from the storage service, for example, a container image, to launch a new function, a new instance. So if we recall that functions are often restricted to be stateless, they usually communicate through storage, which is the same storage service as clouds use for other purposes. So to reason about the overall performance of serverless clouds, we devised the method and tool chain to analyze the performance of each of these fundamental components in isolation. With this insight, we introduced STeLLAR an open source framework for performance analysis of serverless clouds. By configuring function characteristics and the load scenarios, STeLLAR can stress any of these components in isolation. And we showcase some of the results by comparing 3 leading cloud providers. So first, we evaluate the response time of warm and cold functions by steering the invocations to these functions once at a time with a different interarrival time. Invoking functions frequently, for example, once per second, results in warm starts, while invoking them infrequently, for example, once in half an hour, causes cold starts with a high probability, where a function instance needs to be spawned before any invocation can be processed. The charts show CDFs on the y-axis and latency in milliseconds on the x-axis, with warm invocations on the left and the cold on the right. And note that the x-axis have different scale because cold invocations are much slower. So one can see that warm invocations are much faster than the cold invocations, but in both cases, variability that we measure as a 99th percentile, or often referred to as stale latency, is not so far from the median. So the latency is actually quite predictable. We now assess the cold function delays in just AWS Lambda, which appear on the worker nodes with different language runtime and using different deployment methods. The charts show latency CDFs as before, and runtime languages are shown in different colors. Solid lines stand for zip deployment, and dashed lines stand for the newly introduced container-based deployment. We notice that Python container deployments are significantly slower and more unpredictable than the others. One possible explanation of this phenomenon is that a Golang program is compiled as a static binary, suggesting that both zip and container image comprise the same binaries that are likely to be stored in the same storage service. Meanwhile, for Python, a container-based deployment shows higher median and tail latencies compared to the corresponding zip deployment. We attribute this behavior to the fact that Python imports modules dynamically, requiring on-demand access to multiple distinct files in the function image. When combined with a container-based deployment method, we hypothesize that this results in multiple access to the function image storage, since containers support splinters the chunks of the image and loads them on demand. The additional access to the image store would explain the high cold start time and latency variability which we observe for Python and container-based deployments particularly. Combination of this runtime choice and the deployment methods have severe impact on the overall performance. So compared to zip, container-based deployments for Python can significantly increase the response time. Next, we study the data communication delays for an application of 2 functions, where one function transmits a payload of a configurable size to the second function. Since these functions are stateless, data is transmitted via storage service, with the first function saving the payload to storage and the second function loading the payload from storage. We capture these latencies with timestamps taken by the user code in these functions. On the left chart, one can see median latency shown with solid lines. A tail latency is shown as dashed lines. On the right chart, the CDF lines are for 1 megabyte and 1 gigabyte payload transfers, respectively. So clearly, storage transfers are slow and have very unpredictable response time. For example, for 1 megabyte transfer in Google, these delays result in 150 millisecond median and around 6-second tail latencies, which corresponds to more than an order of magnitude gap between the tail and the median. So we identified 2 bottlenecks, which are common for all 3 clouds. And there are more of these bottlenecks studied in the paper, so take a look if you are interested. And we would like to focus on this data movement problems. So the first problem is related to loading function initialization state from the storage which is at the cortex of the cold start problem. And the second issue related to the data movement is related to the cross-function communication, which has to happen through the storage, which contributes a lot to the median and the tail latency. So for today's systems, there is a huge headroom for improvement for both of these issues. And it's fair to say that today's clouds are bound by data movement. So this is the problem that we targeted first in our research. So if there are any quick questions, we can take them now.
Yeah, I have a quick question. So when the reason I think that storage is external is to enable scaling to keep functions stateless. So did you evaluate actual scaling of function, not just looking on latency of execution? So like what happens when you increase number of invocations like 1,000 times and, is storage becoming bottleneck there, or keeping function stateless is actually keeping scaling very nice? And also cost, because if you look on it, the cost is maybe the most important thing about performance. I can buy, like dedicated instances and whatnot, and I get very low cold start and maybe dedicated storage, but then I will be paying a lot, and also I cannot scale that much.
This is an excellent question, and we actually did experiments with burst invocations where we invoke the same function like 1,000 times in a short period of time, and we actually see completely different behavior from different providers. But it's not the storage which becomes a bottleneck. It's usually the way people structure either the placement service or the scaling, like a cold start, because it's easy to have a caching layer in front of the storage. However, it's rather easy to have a caching layer, but all the providers have different ways to deal with scaling. So this is what we observed. And regarding the cost, this is an excellent question. So I'll talk about it a bit later. For real world workloads, which we consider in one of the works, the cost of transmitting ephemeral storage is comparable with the compute costs of function execution. So we notice like 30 to 60% of the cost going into the storage costs. And we are talking about S3, which is rather slow storage. So cost is definitely a problem.
Okay, thank you.
Thank you. So I see there is like quite a lot of activity in the chat.
Sorry, I worked on the Google infrastructure. This is fascinating to see measured from the outside.
Actually, we have, like, this is an overview, overview talk. So we can go as deep as you like, actually, and we can have, a much deeper dive together with you and your team.
I'm not working at Google anymore, but it's really interesting to see. Lambda actually has a slightly different architecture than Google Cloud. I don't know what Azure's internal architecture is, but I linked to a YouTube video. AWS has a great how Lambda works talk from reInvent 2018. So if anyone's really into this stuff, that's definitely a video to watch.
Yeah, for sure. Just to share. Yeah, so, and we also compared like 3 providers, so you can actually see which provider is stronger in which sense. So.
Quick question I have, because you said the communication happens through storage. I'm going to assume that not all communications happens through a storage. Like you can just do an HTTP call potentially to another function. Do you measure those things?
Yeah, we do measure. So the problem with inline communication when you put arguments in the HTTP packet is that it's limited. So you cannot transmit a lot of data. So it's usually like several megabytes. And another problem is that it really limits the function execution model. So you cannot efficiently support scatter-gather patterns, for example.
I see. So I guess to clarify, you're saying using the storage lets one function spin down and another one spin up, unless you get better pricing and so forth and so forth.
Yeah, we're going to talk about it in more detail, actually. So.
Okay, great.
All right, cool. So STeLLAR allowed us to pinpoint and evaluate the data movement issues at the component level. So now we need to dive deeper into this. So what we did is we tried to analyze the tools available for serverless research in like open source academic environment. So what we looked at is first the production serverless deployment, and these systems feature complex distributed software stacks with many proprietary components. And on the other side, the tool chains which are available to the academic researchers, they are insufficient, and academics often focus on distinct components rather than complete systems. And also many prototypes rely on technologies like containers, while most providers, like at least the biggest providers, they moved on to lightweight virtualization. So it's not entirely representative. So what we had to build is a complete open source framework for serverless research. The good news is that there's so many companies which open source their key components, and we integrated them in a single representative framework for serverless experimentation. So we adopted Knative and Kubernetes as a function as a service programming model and the orchestration framework. For sandboxing technologies, we support Firecracker and Java micro VMs along with the vanilla containers that Knative supports. And for lifecycle of micro VMs and other control plane messages, we support Containerd, just like Knative. And gRPC is used across the whole stack, which comes with a lot of advantages, for example, for metrics collection and profiling. So what vHive framework today is, it is representative of production clouds, and it includes only open source production grade components. And what we are actively working on and keep expanding is the tool chain for holistic benchmarking, both end-to-end and per component, which includes a representative suite of the workloads, distributed tracing support, and also full system cycle accurate simulation support in vHive CPU simulator. So vHive allowed us to innovate in 3 different system subfields, and this talk will focus on 2 works only. So the first one is innovation in the operating system and cold starts, and the second one is actually the communication. So let's start with characterizing the cold starts. So cloud services commonly experience frequent changes in internet traffic, and serverless workloads are no different. So it is essential for the cloud infrastructure to monitor the load and timely react to its spikes by quickly spawning new instances of overloaded functions. This problem is commonly referred to as cold start problem. And we'll look at the problem from the data movement perspective and ask the following question: what fraction of data is actually necessary to move to start a function and let it run quickly? Also, if it's common for the functions to experience cold starts, can we learn something from the past invocations to accelerate the future ones? And vHive was a great platform to drill down to the fundamental root cause of this issue. So we built a system which mimics AWS Lambda, which is the leading serverless offering today. And as we discussed previously, at a high level, the response time of a function breaks down to 3 categories. First is the time that the scheduler takes to select the worker host to launch a new instance. And according to AWS, this is the shortest and most predictable delay. So I actually exclude this from the analysis. Even though in Knative it's not the case, it's still quite long. And the second one is the second category is related to loading the state from the storage. And this depends on the function instance isolation technology. And the third phase is actually the processing. In our experiment, each function runs in the firecracker micro VM, like in AWS. And the state-of-the-art method of loading a micro VM from a snapshot works as follows. So the snapshot is taken when the micro VM has a function instance which runs inside and is completely ready to serve invocations. During the restoration, first the hypervisor loads and restores the state of the virtual machine monitor and the emulated devices. Second, the hypervisor maps the guest memory file into the main memory without populating the memory contents, and this is important. And then the hypervisor resumes the execution of the virtual machine from the point at which the snapshot was taken. And finally, the micro VM manager establishes a connection with the function inside the virtual machine. So it reconnects to the rest of the infrastructure. Note that the last step is not essential for virtual machine restoration, but it is required for the serverless case. And after this, the function instance is ready to process an invocation again. So the data movement happens in these 3 phases. So this is where we're going to take a deeper look at right now. So we characterize the latency breakdowns for a number of Python functions in the case of warm and cold invocations. On this chart, you can see the measured latency breakdown as pairs of stacked bars for each function type, with left bars showing the warm invocation latencies and the right bars showing the cold invocation latencies. And you can notice that the right bars are much higher than the left bars. And particularly, there is a big orange fraction, which is related to establishing a new connection, which is not even visible in the warm case because it's not there. And second, you can notice that the green part, which is function processing, increased by an order of magnitude. So what is the actual issue here? And the deal is that these functions are written in Python and use quite a lot of different functionality inside the guest operating system. For example, the guest networking stack. Now we should recall that Firecracker doesn't populate the guest memory with its contents from the snapshot, and instead it relies on lazy paging, which results in a series of page faults arising after the function resumes its execution. These page faults are processed one by one and take a lot of time because many of them require retrieving their contents from disk. That's why we found that the disk accesses upon the page faults dominate the whole Cold-Start latency. We traced these page faults and found out that the following key observation. When functions execute, they touch almost the same set of memory pages, which means that the function have stable working sets across invocation. So now if you imagine that like a function which rotates an image, it kind of makes sense that whether it rotates a cat image or a dog image, it will still engage the same Python modules, for example. It's the same networking stack and so on. So this led to an intuitive solution to record and prefetch the memory pages from this working sets of for each function. Our record and prefetch solution called the REEP snapshots consists of 2 phases. First is the record phase, where upon the very first invocation, the system intercepts the page faults and loads them into the guest memory on demand, while at the same time, it captures these pages as a working set file. And after the invocation processing is finished, the captured working set is written back to storage. Now, all invocations from this after the first one enjoy the expedited prefetch phase. So first, the entire working set file is read from the storage in a single I/O operation. Then all of these pages are installed eagerly at once into the guest memory. And this allows to avoid the bulk of the page faults, except for the rare accesses to the pages outside of the working set, which are still retrieved from the storage on demand. And this way, REAP snapshots accelerate all the cold start after the first invocation of the little, at the cost of the little extra storage. So this plot shows the cold start latencies of different functions. Each pair of bars corresponds to a single function type. And in each pair, the left bar stands for the vanilla Firecracker snapshots, while the right bar stands for the REAP snapshots. First, one can see that the REAP significantly reduces the time of restoring the connection between the function server inside the micro VM and the rest of the infrastructure, showing the efficiency of prefetching the networking stack and the commonly used and reused code. And second, the function processing fraction is reduced by more than 4 times on average for all these workloads. And the overall speed ups for all these functions are significant as well. So it's a software technique which delivers a multifold acceleration. Quite impressive. And this all comes with small extra file being recorded. So the way it works is that we found that it's the lazy paging which causes the long series of page faults. And what REAP does, it introduces selective, eager pre-faulting by moving the working set pages all inside the guest memory at once, exploiting the trade-off of just a little bit extra storage for this working set files to get rid of the bulk of the page faults. And this is already supported in AWS Firecracker. They do support like user page fault handling, which, however, they don't really open source. They only only Firecracker hypervisor code is available. So if there are any questions about this, I'd be happy to take it.
Okay. I had a couple of questions over in the chat. This was running on vHive?
Yeah.
Were the container images already prefetched locally onto the disk for the timing?
Well, in this case, it was just loading the snapshots, right? So the dev mapper snapshotter was already full. So
okay,
it was not on the critical path. Yeah.
I was looking at the cold start times, and I was wondering if that included the time to actually fetch the container image, or if that was pulled out of the graph.
Yeah, this is actually a great question. And like in the production system, this would be another fraction as well.
There's also some work with containerd and CRIO to fetch Docker images on a sort of lazy basis, on demand, basically. Because if you use the default mechanism, you need to pull down and unpack all the tars and write them all out to the file system before you can start your container.
Yeah, this is
another cold start hit.
Yeah, absolutely. So with the guest memory, like with snapshotting, the dev mapper should not be on the critical path, but it can be for for parts of the file system which is not memory mapped. And that can be a big hit because like Docker images are compressed all over the place and across the board. So decompression takes way more time than, mmap and even page faults. So we need to restructure that part.
There's a StarGZ effort that attempts to restructure that compatibly within the Docker ecosystem, but it sounds like these had already been unpacked into Firecracker memory maps things.
Yeah.
Have you looked at sharing those learned maps across nodes?
So this is something that we're just about to merge, actually. So we're going to merge the support for that. And then we actually wanted to explore how this extends to multi-node setup. And it's very interesting as well, because there is a lot of cost trade-offs, performance trade-offs all around that.
If you can store both the memory mapped things and those prefetch maps in shared storage, you can get a lot of scalability.
Exactly. Yeah, indeed, but the most simple case, you just store them together, basically. But obviously, like, we can take a look at how to scale it better.
Yeah, that was my question about, like, are you moving snapshots across the worker nodes? It's interesting. I'm glad you're thinking about that. One thing I was going to ask, but then you answer it here about, like, I'm surprised the page faulting seems to be just like a firecracker issue. And I'm surprised, like, is there a reason? I'm assuming there's a reason why they didn't introduce the, like, rehydrating the guest memory, right? Do you know what that reason is?
Well, it's not a firecracker specific issue. It's just related on, the host OS relying on lazy paging across the board, right? The lazy paging is a default policy. So if you
the copy on write.
Yeah, exactly. So if you use divisor snapshotting, you would probably also have, like, either lazy paging or eager paging, which means moving everything, which is also suboptimal, as we find. So,
Dave, were you asking about snapshotting the actual guest memory, including the Python application?
Yeah, that's what I thought. I guess to clarify, what is in the snapshot is probably useful for me to know. Are you including the guest memory or just the, like, just the app, essentially?
It's the subset of guest memory pages, and the hypervisor doesn't need to know what's inside. So we're completely dumb and oblivious to what we snapshot in this working set files. But it's it's going to be the modules and the libraries which are touched upon the invocations. For example, not the ones which are used which are touched during boot time, for example.
But if you're using, for example, Java, this wouldn't capture the JITted code after hotspot, would it?
That's a good question, actually. So I think this question is how much the applications evolve, right, during their lifetime. And there is nothing preventing us from recapturing, updating this memory pages and so on. And also, if the updated code resides in the same exact guest memory pages, then it's going to be reused naturally.
So one risk is that you might have processes that are, for example, each creating their own cryptographic key. And all of a sudden, you are reusing those, and depending on your AES ciphers, that can be catastrophic.
That's 100% true, and this is not something that we add to the security problem, to the security model. This is an inherent problem for snapshots in general. And actually, AWS is working on this issue. They are aware, and there's, like, more issues related to that. There's, for example, STeLLAR is also compromised by default.
Yep.
So there are a bunch of stuff that needs to be fixed. And as far as I understand, AWS folks, they already start patching Linux, at least for random generators.
I would love to find a standardized way to do this and to fold that into Knative. But yeah, ASLR is address space layout randomization.
That's exactly right. I can just point you to one of the archive papers that AWS folks published, and they at least enumerate the problems and the patches that they were in work this last year.
That would be very interesting.
Yeah, definitely. It would be good to actually somehow connect to the community, like, to exchange, more information, maybe questions answered and so on. I see a lot of, like, good questions and reactions. So I'd be happy to have more of these discussions. All right, so let's talk about the communication now. So serverless workloads are diverse, and many of them have a lot of communication, as you know. So to devise a solution for fast cross-function communication, we need to account for special characteristics of serverless programming mode. First, functions are stateless, and they cannot hold state or share it directly with other functions due to scalability requirement, which people pointed out before in the talk. And second, functions may have any number of instances at any point, each of which are identical, and they are able to process any invocation. So this leaves functions to communicate only through an external storage in the general case. And there's a fundamental contradiction here, because serverless compute scales purely on demand, and it is stateless, but it has to be coupled with a classic stateful, always-on service, which is storage. And as a result, often the storage people choose, like S3, it's slow because it's not devised for such workloads, and also it's pricey. And like for the workloads we consider, it's up to 70% of the cost. So this fundamental contradiction raised the doubt that a truly serverless system should actually require an external service. So let's try to understand why. Let's consider the same video analytics service, which I presented in the beginning. The first function decodes frames from the video fragments coming from the camera, and invokes the second function for object recognition. So in serverless, the deployment of these two functions would look somewhat like this. So first, let's assume that the service has been operating for a while, so there are already active instances for each of these functions. And everything starts with the decoded function producing a frame in which it wants to recognize objects. The user code in this function has to store this object in the storage, and then it triggers the invocation sending the HTTP packet to the scheduler again, specifying the key from the storage. The scheduler then receives the invocation and forwards it to the least loaded instance of the second function based on its own metrics. The function starts processing by retrieving the object from the storage. So now, if you look at the sequence of these actions, it is clear that the real fundamental problem is due to the fact that the decode function instance, which is the source of the object transfer, doesn't know the destination of this transfer. And that is why an external storage service needs to be in the path. But it is the scheduler which makes the decision on selecting the instance of the second function. So the key idea is to delay the transfer until the scheduler makes its decision. So we introduce a technique called XDT, or Expedited Data Transfers, which enables communication without storage. Again, so a decoder function instance produces a frame, and then the user code invokes the second function directly with the object as an argument, which can be a heavy object. And then the runtime in that decoder function instance keeps this object buffered in memory of the decoder function, creating an XDT reference. The runtime then replaces the object in the invocation request with the XDT reference, and then forwards it to the scheduler, this lightweight packet with the object stripped. And like in the baseline case, the scheduler chooses the most appropriate instance of the recognition function and forwards the invocation to the runtime inside that instance. The runtime, before transferring the control to the user code, it fetches the object directly from its source in the decoder function and replaces the XDT reference with the object itself. After that, the recognition function can process the object. So this way, XDT achieves direct object transfer communication in conjunction with existing autoscaling load balancing, which is driven by the scheduler. A few words about the implementation. So the key design principle of XDT is in separating of serverless control and data planes, which we implement in XDT SDK, which is kind of conceptually similar to AWS SDK that is used for packaging the functions. So at the transfer size, at the transfer source, the SDK offers the same API as the baseline system, invoke API or get put API, transparently extracting all the large objects from the control plane requests, the invocation itself, which still goes through the scheduler, whereas the heavy objects go through the expedited data plane. And at the destination, the SDK reassembles the original invocation with all objects before passing the control to the user code. So note that the objects are allocated inside the memory of the source function instance and add no extra footprint compared to the baseline. Transparent data plane separation allows cloud providers to choose any protocol they want for the data plane, depending on their design goals and available hardware. For example, high performance RDMA. This way, XDT allows wire speed direct transfers while keeping the legacy function invocation API. So we evaluate XDT using 3 real-world applications, data-intensive ones, each of which features different communication patterns like scatter, broadcast, gather, namely video analytics, ensemble model training, and MapReduce. And here I plot the latency breakdown for a single request going through each of these workloads, workflows. Each of the workloads, as you can imagine, have several functions, each of which has compute phase shown in orangish colors and communication phase shown in the bluish colors. So you can see that for all the workloads, XDT significantly reduces the communication pattern, accelerating overall end-to-end execution for all of these workloads. So to recap the system design lessons here, the key problem why modern serverless systems require functions to communicate through an external storage relates to the fact that it is the scheduler that makes decisions for the destination of the transfer. So XDT delays the actual transfer until that decision, effectively replacing eager storage-based transfers with lazy transfer, but through a high bandwidth, low latency fabric. So the main takeaway from this work is that storage is actually not required because the data can be buffered at the source and quickly consumed and recycled by the destination. So I would be happy to take some questions here.
Just an observation I have, and I'm kind of curious if you dug into the thing. Like the problem you're describing looks to me like a streaming problem in a way. Have you compared, would I want to run this in a serverless fashion, or do I want to run it in like a classic whatever people used before, like Apache Storm, we have topologies, or Heron is like the new version there. Like, is the functional benefit, like, I guess, what would you, like, given the use case, if I know I'm going to have a continuous stream of video and I need to do processing, should I use classical approaches, is maybe what I call it, versus like a serverless approach if we're not going to be scaling down, right?
Yeah, this is an excellent case. This is an excellent question. And the answer is that in this case, we do support complete scale to 0 as compared to classic approaches. So I just showed this simple, warm everything case, but you can imagine that cold starts can be overlapped with data transfer for further efficiency. So we deliver efficiency similar to a streaming system with the scale down capability. But it's a great notice. This is like a common serverless systems. They are not compatible with streaming services. But with XDT, where we decouple the data transfer from their transfer of references, XDT references, then we can steer XDT reference through streaming engines like Kafka, and then scatter, gather, reconcile, join, and all of it is totally possible. So this is something that we plan to work on in future.
I understand why S3 is an attractive target for that kind of storage, but have you looked at using less durable but still external storage services like Redis or Aerospike or something like that, and how that compares? Because yeah, S3 does a lot to make sure that once you've handed it data, before it returns, it's actually landed on some disks somewhere in a way that you won't ever lose it again.
Yeah, this is a great question, and the answer is XDT can perform better than Redis. We actually evaluate XDT, we have been evaluating XDT versus Elasticache, which is Elasticache Redis from AWS, and we can perform better because it's fewer network round trips, and we are not bound by the Redis replica itself. If you scale your producer instances, consumer instances to tens, hundreds, and so on, you can scale your bandwidths together. So now the question is how to organize the programming model so that we can have continuous scaling of compute, and then you get the bandwidth scaling automatically essentially.
May I just interject here real quick? Thank you, Dmitrii, so much. I know people are going to have to start leaving as we've only got about a couple minutes left. May I just go ahead and launch the polls real quick? I'd like to just make sure that we get feedback from as many people as possible. So I'm going to launch these. If everyone could just please answer these two questions. And then we will hand it back over to Dmitrii, as well as to Evan and Carlos and any other TOC members or anybody else who has an announcement that they would like to make for today's meeting.
I guess, are you saying vote for the TOC election? If you're
maybe that is the announcement.
That's what I'm assuming. Unless there's another announcement that I'm not aware of. Deadline to vote is Friday, but vote today. You'll get a cookie. And if you think you might be eligible to vote, you can try logging into Electo and it will tell you. Also, if you've been doing a lot of stuff with the Knative community and you aren't listed as eligible to vote, which means at least 50 interactions with one of our GitHub projects, let steering know ASAP and they might be able to do an exception, but obviously that would be very last minute given that voting closes tomorrow.
Yeah, you can file an exception. People contribute in many ways that are not counted with the methods that we use. So yeah, you can file an exception. Another announcement is KnativeCon was a one-day event, happened during KubeCon last week, and the videos are available online already. So if people want to watch those, you can go ahead. And also there's other Knative talks in the main schedule by others. I think that's it.
Is the chat going to be visible and available when this goes up on YouTube?
Yeah, I'll make sure that that is included.
Great.
I guess, Dmitrii, do you
see
have
a
more?
lot of positive feedback. Yeah, we have some more, not a lot. Actually, we had some questions for the Knative, engineers, which can help us in further research. Like
I think
maybe it
some
would
of us
take
can
like
stay
10
for a
more
few
minutes
minutes
of your
if
time.
you want to ask them now, or you
Yeah.
can follow up on the mailing list.
Yeah, we have some former researchers.
Cool. Yeah. And we would actually appreciate connections to like people who work on this thing and like many feedback.
Dave over there. And you can talk to me too, but Dave is the working group lead, and Paul as well is on his way there, I think, on the serving side of things.
Okay, maybe members of our team can put down the names and we can contact this.
We also have a weekly meeting. It alternates. So for example, I think like today we cancel it because of this meeting. It conflicts, might shift it around, but it's on the Knative calendar. So there's an alternate. This is where the timing doesn't work out for EU. So essentially like maybe what I'll do is I'll shift if you pick a date, I can shift that meeting earlier to accommodate European time. Yeah, because right now it kind of favors like one time zone favors Japan, which one of our contributors is in, and the other time zones just favor kind of the majority, which is like Eastern and West Coast time. But if you want to ping me, it's just dprotasso on the Knative Slack. I can, and like with the date, I can shift that time to accommodate your team if you want to have it. So I think for the majority part, like a bunch of us are mostly like Eastern and West Coast. So maybe like a 10 o'clock start is not too extreme for us, or 9, and might be okay for you. So
yeah, for us it's perfectly fine.
Great.
Yeah, we can arrange like further meetings on like particular topics basically.
Yeah.
So yeah, I just want to mention like what we are gonna work on, like what we are working on right now, like a bit further, is that we are actually looking at the scheduling space, and we are working on the methodology to replay traces from production clouds like Azure Functions into like small scale clusters, so that we keep all the characteristics of cold starts and memory footprints and so on. Another is that we have a benchmark suite that is called vSwarm, with a lot of like more than 40 workloads right now, like small functions, like multifunction workloads and so on. And we also look at simulation of the hardware and plan to extend to emerging clouds like Edge, but we haven't found Knative enabled platforms for now. So if there's any feedback from that side, it would be great. And I think there were a few questions that we wanted to ask. So so far we focused on cold start, communication, efficiency of the hardware where functions execute. So are there any other directions that you think we may address in future work?
I have one. I was asking it before, but did you look on, you had this diagram where Knative and then all other systems that are public cloud serverless, but there are today Knative API compatible systems like Google Cloud Run. And I think there are 2 versions, and there is also IBM Code Engine available. So, and they are all serverless, and you can run, I think, all those workloads on them. But it'd be very interesting to find out, how do they compare, or is those optimizations, I don't know, latencies or apply?
Yeah, that's a great point. Yeah, like obviously with all these platforms, we have visibility only to like some of the user level infrastructure. Some optimizations that we do, they need a further deeper visibility or modifications to like hypervisor or like queue proxies, for example. So XDT, we basically implemented the queue proxies and the SDK. But some of it is possible, yeah. Good point. Thank you.
Because then you're comparing more orange to orange, where I think it is very difficult if you are just running black box, and then on the other hand, what is the other box?
Yeah, that's actually excellent point. Yeah.
Do you want me to answer any of these questions on here? Because I can answer 2 or 3 of them for you if you want.
Yeah, sure, absolutely.
Okay, so I can probably start at why Knative allows container concurrency greater than 1. Knative evolved out of Google App Engine and also looking at some other platforms like Cloud Foundry. And in a lot of those, they allow you to run a full-fledged application. And as you noticed, cold start can be a little bit of a pain. And also, if you allow only one request at a time, you have to scale really high in terms of concurrency and also cost. But a lot of the time, these functions are doing things like make a network call and wait. So there's actually a lot of opportunity for overlap, assuming you're not doing something that's pure compute.
And Lambda allows for more than one request at a time if you configure it, I think.
Does it?
I think it was something in the last 2 years. Let me double check.
Okay, so historically, AWS Lambda had a model where the worker calls out to the controller process, and it could only have a single, basically, ticket in flight at a time. This allows you to do some simplified programming models, like having globals, and not have to worry about it. It sounds like maybe in the last couple of years, they may have relaxed that somewhat, but by default, they started with one, and that gave a simpler programming model. And if you know there's only one request in flight at a time, if you see an outbound connection, you know it's associated, which request it's associated with. Whereas if you have more than one container request at a time, and you see an outbound request, you don't know which one the request is associated with. Unless you do some really fancy, ugly stuff that Google App Engine did early on, but I don't recommend it to anyone.
They also mentioned to me, like we talk with AWS, they mentioned security implications of running several requests within the same memory, essentially.
Potentially, but you can also run into the same problems if you reuse a container for more than one request, and they do that. So.
True.
But yes, if you don't do locking or things like that, then it's easy to get corruption and crashes and stuff like that. Whereas if you restrict it to one request at a time, it's real hard to screw that up. The next question was about a Knative worker running less than 200 pods, while AWS, their workers will do 1,000 or so. It's in those that AWS internals talk. So Kubernetes assigns an IP address for each pod. And the default Kubernetes IP address layout restricts you to about 110 pods, which is a kubelet level flag. Theoretically, you could do lots of big workers by changing a bunch of Kubernetes level flags. In practice, very few people do that. But it's due to IP address limitations in Kubernetes. And yes, the Kubernetes scheduler is a bottleneck. We've talked about what would it look like to change Kubernetes so that you could pre-schedule a pod, but not start it yet, and lease those resources back to the kubelet for lower priority tasks. That's going to be a major engineering effort. My estimate would be 1.5 to 2 years for 4 to 5 engineers, at least one of whom is pretty senior and deep in the Kubernetes ecosystem. So yes, we're aware. Yes, it's a blocker. Also propagating IP address decisions in Kubernetes also ends up being part of our slow path, because you don't know what IP address a pod is going to have until it's assigned to a node, and that node CNI has made a decision about that IP address. And then whoever's upstream, like the activator that needs to call, needs to find out what IP address that pod decided on. So if you could either have the activator be on the same node so that the latency for that was near 0, or if you knew that IP address in advance, which starts to hit you up against those IP addressing limits. So
yeah, that's a very good production points. And we are actually actively looking at the scaling right now. And we are trying to understand the bottlenecks, and we are trying to see which policy we should use, like from the queuing theory perspective, for
if you're looking at that for Knative, I'm going to point at people who may not be the same position. But Nader, I don't know if Nader, if you want to say hi or anything, Nader is working on the auto scaling and measuring that more deeply.
Yes, hi. Yeah, if when you get into more details, we can talk about it more.
Well, actually, our team would love to have an extended discussion on this front. Like, I actually had to hold their hands a little bit to, ask more questions.
We're friendly. We don't bite.
Yeah, if you come to
That's great.
the surveying working group, you'll find all of us at the same time. It's probably the best time to start, and then we can like have other meetings started, like pick it up from there.
Yeah, amazing. That's pretty much what I wanted to talk about, and thanks a lot. I hope it was interesting, and we have a lot of projects in flight, both in Edinburgh and in the TH, and vHive is getting a lot of popularity. So actually, yeah, join the community, follow us, and see how we can do knowledge transfer, for example, both ways.
Thanks for coming.
Yeah. And there's a link to the different working groups in the chat too. So if you save out a copy of that, you will be able to find where to find all these folks.
Like in a DM, probably I need some kind of
you can DM me on the Slack, and I've got I will have a file of all of the at least public chat messages.
Exactly, that would be perfect. Yeah.
If anyone's been back channeling, it won't be in there.
Great, thank you.
Okay.
Wonderful. Well, is there anything else before we close? We've run a bit over, but I think this has been a wonderful discussion. Everybody good? Going once?
Yeah, I think we can close. And thank you, Greg, for hosting this first time meetup. Appreciate it.
Yeah, it's my pleasure. Yeah. Wonderful. Okay, I will stop the recording.
Thanks.